Hi, everyone. My watch says it's 4 o'clock, so let's get started. We are excited to have Chris Pauly joining us remotely today from Fermilab. Chris is a spokesperson for the Muon g-2 experiment, which you will hear about today. And I won't give away the results, but it presents a major outstanding mystery in particle physics. Chris did his undergraduate studies at Missouri University of Science and Technology and obtained his PhD in physics at the University of Illinois. He has been a co-spokesperson for the Fermilab Muon g-2 experiment for the last 3 years, which has been a very exciting time for that collaboration, as you are about to hear. For his work with this experiment, he just last month won a Falling Walls Award in physical science. We are all sorry that Chris couldn't join us in person due to COVID-related travel complications, but let's all make him feel welcome. Chris, please take it away.
All right, thank you so much for the warm welcome. I really was looking forward to visiting Pasadena again. I would have loved to have been there in person, but the travel restrictions, especially with the national labs, are so up in the air that in the end I decided not to brave it. But who knows, maybe next year when we publish our next version of this result, I'll come out and be able to present it to you in person. That would be great. I should also say I'm technically a former co-spokesperson of this experiment now, because under my tenure as spokesperson, we passed a novel thing called term limits. So for those of you that are big fans of term limits, I sealed my own fate at 4 years. And we've recently had Brendan Casey take over as the co-spokesperson with one of our Italian representatives, Graziano Benanzoni. But anyway, hopefully many of you heard about this result because it really was the result heard around the world. It was really phenomenal, the amount of coverage that we end up with for such a small little experiment. At the end of the day, I think over 3,000 media outlets ended up covering this story, which is pretty amazing if you think about it. It's not often that results from particle physics can really capture the mainstream media attention at this level. Phenomenally, Fermilab does a thing where they add up something called media reach of a news story, which is essentially the subscribers or the total number of people that had access to that news story with whatever outlet it was published in. They estimated that 6 billion people on the planet had exposure to the story, which is pretty good relative to the Earth's population of 7.7 billion. Maybe I have to check their numbers because it still sounds too good to be true. But it's been great. The Nobel Prize Committee even caught wind of us. They invited us to present the results at the Manny Sigmund Memorial Lecture in Stockholm. It's the first time particle physics has done this since the discovery of the Higgs. So it's nice to be getting the attention of the experts as well. And perhaps most importantly, you've made it in the upper right here when Luke Skywalker starts tweeting about you. So it's been quite a ride. It's really, really fun result. And the interesting part, as you'll see, is we're just getting started on our analysis. So just to give you an idea of the timeline here, this is a slide from the very first Fermilab colloquium back at a time when we were just starting to talk about how we might take the Fermilab accelerator complex, which was going to be shutting down, the Tevatron, the collider program was going to be shutting down soon. And we started talking about how can we take this facility and this $100 million worth of equipment that suddenly will become available and really build a future set of transformative experiments that can really utilize all that infrastructure. At the time, there was a very well-developed proposal for an experiment called mu-DE. Some of you know it quite well. Caltech are big collaborators on the mu-DE experiment. And working with our mu-DE colleagues, we really figured out how to synthesize the two experiments into one program that we call the Muon Campus. And you can see this was the vision for it as presented back in 2012, which gives you an idea of how long it really takes, to get an experiment proposed, funded, designed, constructed, data analyzed, and published. So, not quite 10 years, but pretty close. So this is a picture of what that rendering looks like in reality today. The part in the foreground that you see with these 3 buildings arranged in a triangle, that's actually what used to be the anti-proton source. That's where we made the antimatter beams for the Tevatron program. We were able to take that whole source and really it was 2 rings. We dismantled both of them. We rebuilt 1 ring, 2 beam lines so that we could deliver the custom beams that we need for the g-2 and the mu-e experiments. So you can see in the background, the building back here on the left is mu-e, the one on the right is g-2. I think you can see it a little better here. Here's a blow up of the two buildings. And so you can see this has become quite an interesting part of the Fermilab physics program with these two experiments. Mu-e, I'm not going to have any slides on that. I'm sure you guys get lots of mu-e talks, but I will say, we're looking forward to passing the muon torch over to our sister experiment sometime in the next couple of years, as soon as they're ready. We're already working with them in the sense that they're commissioning their beams and they're really getting ready for the start of their experiment as we're sort of entering the twilight phase of ours. So for those of you who might not be particle physicists, we'll just start at the beginning and talk a little bit about why we use muons to begin with. So first of all, they are one of the fundamental building blocks of the standard model. You can see them down here arranged in this sort of pictorial representation of all the particles that we know about. The muons we lump down here by the electrons, because of course they're very similar to electrons. As far as we know, they're point particles. They have the same electrical charge and they have the same spin properties. But there are some very important differences. So first of all, the muons are about 200 times more massive, which makes them uniquely sensitive to new physics processes compared to similar searches you might try to perform with an electron. You could extrapolate all the way up to the more massive tau and say, well, that would be even better. But then you get into problems with it being so short-lived that it's hard to do precision experiments. So the muon is kind of in a happy medium there. It's unstable, but it still lives 2 millionths of a second, which doesn't sound like long, but compared to modern day electronics and our ability to track particles, it's quite a long time to do the experiment. And as you'll see in a little while, our experiment uses relativistic muons, so ours actually live for 64 millionths of a second. So we get some luxurious extra time in there to watch them. So after 2 millionths of a second, if you start with a positively charged muon, it will decay into a positively charged electron or a positron, and you get two neutrinos that go shooting off into the cosmos. In our experiment, our detectors actually see the positron flux that emerges from the muon beam, although we do have beamline instrumentation and so on that can also directly see the muon beam. So the reason we're really interested in this muon magnetic moment is, because of their spin and charge, you can sort of think of muons as acting like little bar magnets. They have their own internally generated magnetic moment. So like a magnet, like a bar magnet, if you put one in a magnetic field, it will experience a torque. When you put it in that magnetic field, it has a potential energy. And so that torque causes the muon spin to process around the magnetic field at a rate that increases or decreases based on two things. The strength of the magnetic field you put it in will make the gyroscope spin faster and faster. And of course, the strength of its own internal magnetic moment will make it spin faster and faster. So in that sense, it's very much analogous to a sort of classical gyroscope that many of us have played with, where you have a spin axis of the gyroscope, but that spin axis itself will rotate around the magnetic field. Of course, in a classical system, that would just rotate up and minimize potential energy. But in a quantum mechanical world, there's no place to conveniently give that energy to. And so the muon will just spin and spin and spin around its magnetic field that it's tilted with respect to. So the strength of the magnetic moment can be written in terms of a few fundamental constants. You can see them here: the charge of the muon, the mass, and the spin. We also like to pull a constant out front that we call the G factor. And that's because this G factor has been very, very interesting and a good way to sort of understand this overall strength of the magnetic moment relative to expectation. So, classically, around the turn of the last century, the expectation would have been that for a muon or for an electron, in that case, since muons hadn't yet been discovered, would be that G would be 1. It was, found sort of in the 20s and 30s that for the electron, the expectation is actually that G is 2. And that's basically comes from folding in relativistic quantum mechanics. It was initially shown by Thomas, and then was also predicted as part of Dirac's famous wave equation that G would actually be 2. But as you can guess from the name of our experiment, which is g-2, there's more to the story than just G equals 2 and relativistic quantum mechanics. And that comes from the fact that particles in the universe are never truly alone. They're constantly surrounded by this entourage of other particles that blink in and out of existence temporarily. Oftentimes you'll see it referred to as the quantum foam or the quantum sea. Every particle that's traveling through the cosmos, even if it's all by itself, is constantly surrounded by this entourage of particles that are just blinking in and out of existence continually. And so what particles do that? Well, all of those particles, all 17 particles in that picture of the standard model that you saw, are able to fluctuate in and out of existence. How often they do it depends on their coupling strength and how massive those particles are. But in principle, they all can do it. So the anomalous magnetic moment is really the part with which that A mu, the anomalous magnetic moment, right, sorry, the part with which G differs from 2. So you see, we write the anomalous part as G minus 2 over 2, because that's the fractional difference. And that's where all the interesting stuff happens, not in terms of the muon's properties itself, but in terms of this quantum foam that's always fluctuating in and out of existence around the muon. So measuring that precession very precisely, or that magnetic moment very precisely, allows us to see if there are, any new particles or forces that might be contributing to the anomaly beyond the ones that we already know about. And so what particles might be doing that? Well, we have good reason to believe from many sectors that there might be additional particles in the universe that we haven't yet directly discovered. Dark matter is probably the most famous of the day. We look out in the universe and we see much more gravitational mass associated with galaxies than we would expect based on the visible matter we see there alone. And it's not a small factor. We're missing something like a factor of 4 or 5 times the mass we would expect to see. And so, there's many theories out there that suggest we're swimming through a sea of dark matter all the time, and we just haven't been able to observe it directly. That sounds strange to a novice, but remember, it was just in 2013 when we've actually finally directly discovered the Higgs boson, which is also a sea of particles that we're swimming through all the time. Supersymmetry is another very common theory. It's a theory that was invoked really to try and understand why the Higgs mass came out to be so light. We knew before the Higgs was discovered that it was going to be a very light particle based on other precision observables that we had seen. We suspected it would come out to be very light instead of, sort of the natural scale, which would put it up at a mass range far beyond where accelerators could reach. But sure enough, we found it where we expect it, but we still don't understand why it's so light. We still can't say for sure that there's only one. And so there's also big questions, coming from that sector. And of course, as experimentalists, although we appreciate the theoretical guidance from our theory friends, we're just always looking for whatever monsters might be out there that haven't yet been imagined and are still to be discovered. So there's plenty of unknown possibilities also. So one of the reasons that makes this anomalous magnetic moment so interesting is because this isn't the first experiment to try and take a look at it. About 20 years ago at Brookhaven National Laboratory, there was an experiment that was conducted to measure the magnetic moment of the muon, and it found an interesting hint of new physics, about a 2.7 sigma significant hint that there was something we didn't understand about the standard model prediction for all the particles we know about that should be fluctuating in and out of the vacuum, and the measured magnetic moment that was discovered at Brookhaven. Over the years, the theory continued to improve since that experiment turned off, and that 2.7 sigma hint grew to 3.7 sigma due to the improvements in the theory. And here you can see how the theory has progressed over the last 20 years. And here you can see that Brookhaven result in the green band. The blue band here shows you what the ultimate precision of our Fermilab experiment aims to achieve. And you can see this white space in between is where those monsters might lie. So because this has been a very intriguing difference for many years, you can see the citations to the experiment. I haven't updated this plot for the current year, but it's also obviously skyrocketed with the new Fermilab results. I really should update this. But you can see it's been consistently one of the more well-cited results in particle physics for the last 20 years because it is a mystery, and people are trying to understand it. We'll talk about some things numerically here. So one thing to keep in mind is that the size of this difference is about 270 parts per. Is about 27 times 10 to the minus 10, which would be 270 parts per billion or so. So it's a very small difference. And so the precision of the experiment is very important in terms of trying to see if there's new physics lurking here. And by the way, I'm just going to keep talking, but if you guys have a question, feel free to raise your hand or interrupt me, and I'm happy to answer questions as we go as well. So before we talk about the experiment, let's talk a little bit about the standard model calculation, because this is an experiment where you go out and you determine the anomalous magnetic moment with this beautiful device with this incredible precision, but your result is only as good as the theory by which you compare it to. Because if we're searching for the new physics, we really have to understand, what our existing particles and forces contribute to that anomalous magnetic moment. And so you can see here, the lowest order correction comes from the Swinger term, where a muon here is just propagating along in space and time. It's interacting with the magnetic field it's in. That's what this photon is indicating. And it can spit out a photon and reabsorb one. That self-interaction term, the Swinger term, is by far the largest contribution, and it is what really causes A to differ from being zero completely. And you can see sort of in the third decimal place here, where the Swinger term starts to contribute. Now, QED, you can see in this table here, these are the sizes of the contributions in units of 10 to the minus 11, and these are the relative uncertainties in the column on the right here. And so the point to take away is, though, although QED is by far the largest contribution, it's also known with such incredible precision that it's not very controversial. QED can be calculated perturbatively. It's used in other experiments like the electron g-2 at an order beyond what we need it for the muon, and it still holds true there. And so it's not controversial. Similarly with weak, the weak contribution is very small at 150 times 10 to the minus 11. But again, because it's all very calculable, it has a very small uncertainty as to its overall contribution. This 153, by the way, should be put in context with that discrepancy from Brookhaven, which is 270. So that discrepancy is roughly double the weak force, double what all the W and Z bosons and neutrinos contribute from those quantum C fluctuations. So it's an interesting, rather large difference, even with respect to the weak portion of the calculation. As another scale of reference, when we finally determined the Higgs mass, this number didn't change at all because we had already pinned it down. It changed by less than 1 part in 153, I should say, once we actually determined the Higgs mass, because it was already known well enough, and it contributes a very small amount to this weak contribution, or relative to the weak contribution. So the controversy, in terms of the theory, all really lies in the quark loops. So here you can see a Feynman diagram that shows a muon propagating along. It spits out a photon, and then you get some hadronic blob in the middle that couples through a photon back to the muon leg. This is the second largest contribution, and it's the largest uncertainty, 370 parts per billion. Again, maybe to set the scale with respect to the experiment, you'll hear more about this later, but the Brookhaven experiment was, around a 540 part per billion experiment, as opposed to this 370 part per billion uncertainty on the hadronic vacuum polarization here. The experiment at Fermilab aims to take that uncertainty down to 140 parts per billion eventually. The other portion here is the hadronic light by light. This is topologically a little different because you can see the photon here that couples to the external field actually comes out of the hadronic blob, and it couples back to the muon through 3 photons. And that is a little harder to determine, as we'll talk about in just a moment. And I want to say real quick, I want to thank this consortium called the Muon G-2 Theory Initiative, because long before our experiment, was even beginning construction, we started talking to the theorists in the community and saying, hey, we really need all the theorists in the community to band together and make a firm prediction for what this magnetic moment of the muon should be, so that when we publish our result, we have something to compare it against. And so this group has been hard at work since 2017. They've organized 6 workshops, and they've been really working hard to understand the theoretical prediction as well. And so any numbers that we quote as experimentalists come directly from the theory initiative. So coming back to this hadronic light by light contribution, it's tricky because it's also hard to calculate. The problem with anything with quarks in the loops is that you don't have a good perturbative theory to do the calculations in. So you kind of need a trick in order to understand what the hadronic contribution should be. The hadronic light by light was pretty controversial in the past because although it's small, it's roughly maybe a third of the size of the discrepancy with the Brookhaven experiment. it was somewhat controversial several years ago, because the only way really to calculate it came through some model dependent calculations. And, unless you're a model builder who spent 20 years of your life building those models, they're very hard for somebody on the outside to penetrate and understand just how reliable are those models that are used for the calculation. They weren't directly measurable at the time, and they relied on these model dependent calculations, but there have been sort of two very important developments. So first of all, there have been data-driven approaches that have been able to measure that contribution. At least about 80% of it, the dominant part of that contribution, has been determined directly through experiment and was in very good agreement with the model builder calculations. The second thing that's happened is the advance in lattice calculations. Lattice is trying to get to the precision that it can do all these calculations from sort of a first principles computer simulation, and they've been making amazing strides. And here you can see plotted on the right, these yellow values are sort of the values that came from the model builders that were people were back when people had uncertainties whether those would be valid or not, whether there was some assumption that was being made that was hard to miss. And then you can sort of see the state of the art in the model building. That was the yellow. But then you can see here also in the blue some lattice calculations that have been performed. And because you really only need to understand this contribution at the 20% level, the lattice has been able to achieve that. And you can see the results are in very good agreement with the model-driven approach. And so that makes us feel good that all that is in very good shape. And so you can take the two values, the one from the lattice, the one from the data-driven dispersive approach and the model builders, and you can combine those together into the world average as quoted by the theory initiative. And you can see it's basically right in line with what the model builders have been saying for the last 20 years. So that's great. Now, the hadronic light by light, it's difficult. Once again, you don't have a perturbative theory to do the calculation in. And now you need to know it at a much, much higher precision. It's not okay to just know it at the 20% level. You can do that with a model dependent calculation for the hadronic light by light, but we need to know this, as sort of, a much higher precision than you can get through that sort of model building. So rather than rely on calculation, for the last 20 years, the hadronic vacuum polarization, even longer actually, has been determined by measurements of E plus E minus goes to hadrons. And the way to think about that is, this is the diagram you'd like to calculate on the left here. But if you sort of split this out and, don't worry about the fact that you got a muon, it's easy to go back and forth from a muon to an electron. But you can see how this goes to a photon and then goes to quarks in the final state. So what we do is we relate this diagram we would like to calculate to actual physical measurements of how often E plus E minus collisions going to a virtual photon end up with quarks in the final state. I mean, really all you need to know is the photons going to quarks. And so you could do this experiment with any photon you could create, but we tend to do it, the way to do it where we have enough statistics and enough control are through, collider experiments where you have an E plus E minus colliding together. So that's a fixed target, and that they come in two varieties. They either run at one fixed center of mass energy, and then you look for a photon that's radiated off because you need to make this measurement as a function of energy, or there's accelerators like at Novosibirsk that actually scale the accelerator energy up and down to map that whole interaction out as a function of root S, the energy in the interaction in the collision. So this relies on some very basic principles, analyticity and the optical theorem, some very basic math principles. And then you do an integral over this QCD kernel that you see here, which ends up being heavily weighted towards low values of root S. So all the dominant contributions that enter here, as you might guess, come from the low mass states, from 2 pion states, from so the lower the mass of the state, the more it contributes to the process. So the experimental inputs to this hadronic vacuum polarization span many facilities. Here you can see all the places that have gone out to make this measurement. Here you can see sort of just plotted as in this graph here, all the various channels that have been measured. The yellow one here is the 2 pion channel, and you can see all sorts of other, higher multiplicity pions. They're not labeled here necessarily, but they're all these various final states you can make the measurement with. So in addition to this data-driven approach, there's also been some very interesting lattice calculations. So the lattice calculations are also starting to reach the precision that they need to make in order to say something meaningful. And so to put this in context, in this plot, you can see in yellow the Brookhaven result, again, the Fermilab, the goal for the Fermilab uncertainty. And down here, you can see the data-driven approach from those E plus E minus goes to hadron measurements plotted with the red in the red points. All of these blue points up here are lattice calculations that are all striving to achieve an error bar that's compatible with the E plus E minus data-driven approach. And in fact, this purple point is particularly interesting because this is a hybrid approach where the RBC UK QCD lattice group said, well, let's take those E plus E minus results and let's map them in such a way that we can take the lattice result where the lattice has a superior uncertainty, and then we'll take the E plus E minus goes to hadron measurements where they have a smaller uncertainty, and let's combine the two wherever they're at their best. And that was the result they got, which looked very good. It was in line with the data-driven approach. But you can see there is a controversy brewing here because all of these points from the lattice do tend to fall to the right. And quite recently, there's been a result from the BMW collaboration that for the first time is pushing the precision to the point that they're starting to become competitive with the data-driven approach. And you can see that falls to the right. And so the theory initiative, this is all very new, sort of within the last year, this development has come up. The theory initiative right now, their statement is sort of, we need to take some time, understand how robust these lattice calculations are. Do we really understand their systematic uncertainties? And so the point you see down here that they quote as the official theory recommended value comes from the data-driven approach. But of course, we're all keeping an eye on what's going to happen with this lattice, and it will be very interesting to see how that develops over the coming year or two. So getting back to the experiment. So the goal of the experiment was really to sort of go back to the Brookhaven experiment, but do it with roughly 20 times the statistics. It turns out the beam at Fermilab is capable of delivering that. The container that was used at Brookhaven was a perfectly good container. So the goal was to basically bring the container to Fermilab, upgrade it substantially, rebuild basically the whole experiment from the magnet up to have instrumentation, to have all the features that we knew were needed to tackle the largest systematic errors so that we could take 20 times the muons, reduce the statistical error down to 100 part per billion while controlling systematics at a similar level. And so some of you have probably seen the pictures. That was quite an adventure trying to get the ring from Brookhaven to Fermilab, because you can see a picture of it here. Once you take this insulation off, there's about 600 tons of steel. And once you take that 600 tons of steel off, what you're left with are these silver superconducting coils. And they're superconductors because you need to run 5,000 amps of current through this magnet. You can't cut them, you can't stitch them back together. So they essentially had to be shipped in one piece. And so that's what you see here is the underlying superconducting coils mounted on this red lifting fixture, because the technical specification was that we didn't want more than 1/8 of an inch bend for fear of damaging that delicate superconductor that had been glued together, 20 years ago, and who knows how good the epoxy is. And so we had very stringent engineering requirements to get the thing transported safely from Brookhaven to Fermilab. Transporting it by land was impossible. Just too many trees and power lines and things you would have to take down for a 50-foot diameter device. So shipping it was really the only way to go. It was too big to fit through the Erie Canal. So we couldn't go through this convenient canal to get into the Great Lakes. And the other way to go sends you around, through some pretty atrocious seas to get into the Great Lakes the other way. And so it was decided by far the safest route was to hug the shoreline and try to avoid hurricanes and take it around Florida and up through the river system to the closest point of approach, which was Lamont, about 30 miles away from the laboratory outside of Chicago. And so here you can see some great photo opportunities that arose of the device, the shrink wrapped on its special transporter. You can see it getting craned onto its own custom barge here. You can see what it looked like in Fermilab when you need to transport something 30 miles through Chicago suburbs. Really, the best option is to use the interstate as much as possible. At least it's the best for us. It wasn't the greatest for all these people lined up behind these 4 trucks. But for two nights in a row, we closed down interstates for about 3 hours just so we could get that container to Fermilab. Some other great shots of the barge coming by the St. Louis Arch. Here it was rolling off of the barge at the Lamont Inn. We had a huge party, you know, something like 3,000 people came out to welcome the ring when it arrived. This experiment has traditionally gathered a lot of publicity. And so we really appreciate all the great photo opportunities that came with this transportation. And then at the bottom, you can see after the ring arrived, this beautiful cloudscape came out. That's not doctored. That's the Fermilab high rise in the background with the ring in the front and this amazing cloud cover that came out. It was the stormy clouds telling us the analysis was going to take 3 years probably. Okay, so here's what the device looks like, all put back together at Fermilab. You can see the beam line comes in through the back here through these orange magnets. We inject the beam of muons into here. When we're running the experiment, we're injecting about 10,000 muons at a time, and we're doing that about 10 times per second, and we're doing that about 8 months out of the year. And we're now entering our 5th year of running. So that shows you how long it takes to really acquire the statistics to get to 20 times the Brookhaven level. I'll say relative to our design goal, our instantaneous flux ended up being about half of what we had projected for a number of factors, 10% here and there that all added up. And so that's why the experiment's basically at a 5-year runtime. But we're getting very close to achieving our statistical goals, so that's great. Just to recap how the experiment works, you can think of muons as little spinning tops that have a magnetic moment. Our goal is to determine that magnetic moment. The muons in a magnetic field will start to precess like this gyroscope. We need to determine the rate of that precession and the strength of the magnetic field that they're in. And this is kind of what it looks like when you put it all together. That's a representation of what a muon looks like running around our ring. It's got its spin vector constantly precessing around and around. It's going a lot faster in this, and I hope you guys are able to see it. I know there's some lag because I wasn't able to be there in person. This is exaggerated. Really, a muon has to make about 29 laps around the ring before its spin vector will rotate a full 2 pi. Okay, so you might ask, why do we use a storage ring to start with? As I said, we inject about 10,000 at a time. They're nearly 100% polarized when we inject them. That's because we first start by taking protons that impact the target that make a pion beam. Because of parity violation and pion decay, all the muons we capture that are very forward going in our beam line end up with nearly 100% polarization by the time we've collected them. The rate that the muon spin rotates with respect to the cyclotron frequency is given by this expression. So let me stop and explain that a little bit. So we've been talking about this muon spin precession, this Larmor precession frequency it's called, but also there's the frequency that the muons go round and round the ring at, the cyclotron frequency. If you take the difference of those two numbers, something kind of miraculous happens. You see, just in the fundamental sort of first order mathematics, the coefficient in the front here turns out to be g minus 2/2, which is the anomaly. That's the fractional difference that g differs from 2. That's the thing we want to know. And if g were exact, and so that's the thing we want to know. So you can imagine if g were identically 2, then this coefficient would be 0, and the spin and the momentum vectors would be forever locked together as you see them in this upper right-hand corner. But because they're different, because of these virtual interactions, the spin starts to get out ahead of the momentum. And so what we really need to determine is that difference frequency. Yep, okay, that's thinking I missed something, but it's on the next slide. Okay. And so just like we rely on parity violation and the pion decay in order to give us the polarized source, we also rely on parity violation on muon decay to give us the polarimetry we need to resolve that muon spin. And the way that works is high energy decay positrons tend to be preferentially emitted in the muon spin direction. So when the muon spin is aligned with its momentum, you tend to get more energetic spectrum than when the muon is anti-aligned. And of course, that switches signs, whether you're talking about particles or antiparticles. But the point is, as you go from being forward to backward, the energy spectrum fluctuates up and down, as you can see in this sort of theoretical picture that doesn't include detector acceptance, full detector acceptance anyway, of how that energy spectrum changes. So if you we array a bunch of detectors around the inside of the ring. We use lead fluoride crystals to have segmented calorimetry, which is one of the big upgrades relative to Brookhaven. Brookhaven just had monolithic blocks, whereas we have this great segmentation. which helps us to resolve pileup errors for those of you that are familiar with that. But if you just draw a cut on this plot, then you get the sort of famous g-2 wiggle plot, where you draw a cut and you look at the number of particles fluctuating above that cut line. It goes up and down, oscillating at this omega A frequency, which is the difference between the spin and the Larmor and the cyclotron precession frequencies. And that is directly proportional to g-2/2, which is A mu, which makes this experiment 800 times more sensitive than an experiment at rest, because at rest, you would basically be measuring G directly as opposed to A mu. And that is one of the tricks that gives us the precision we need to get down to a precision where we can start to ask if there are new particles, new forces in the universe. Storage rings also come with some complications, though. First of all, we inject them and the magnetic field keeps the particles confined and moving around, keeps them radially confined. But if we didn't do something, they would just spiral up or they would spiral down because, when we inject them, they have some small, vertical angle to them, and they would just spiral up or spiral down and get lost before we can make the measurement we need. And so we have to superimpose an electric field. And that electric field, as you can see here, can also cause the muon spin to precess. Because, for a relativistic particle moving in electric field, an electric field looks like a magnetic field. But again, due to somewhat of a miracle of nature, you can see this first order coefficient in front of this expression involves A mu and the relativistic gamma for the muons that we're looking at, their speed. So quite strangely, if you choose your muons to go a certain speed, in particular, if you choose gamma to be 29.3, because of what A mu happens to be, this term goes to 0, and it suddenly doesn't matter that you have an electric field. And that's important because we work very hard to make a very uniform magnetic field, but in order to have a confining electric field, it has to be a quadruple field. It has a large gradient in it. Plus, electric fields are harder to determine than magnetic fields. And so if it weren't for this trick of running at gamma equals 29.3 with our beam, we wouldn't be able to make the measurement at the precision we need, which is another one of the sort of miracles of the whole, what makes the experiment really so elegant. So in addition, because of this electric field that we add and because of the magnetic field confinement, the muon beam swims both vertically and horizontally. And in fact, all the muons that we inject, all 10,000 of them that we do at a time, they start out doing that coherently. And so that leads to beam motion, which can then detect, couple the detector acceptance effects because your beam is moving back and forth as as it goes by the detectors. So we have to account for those kind of effects in the detector acceptance and, how they actually change omega A to the extent that this term isn't identically 0, for instance. Okay. So as I mentioned earlier, we also need to know the magnetic field. We need to know this precession frequency, but we also need to know the magnetic field at better than 100 parts per billion as well. And we use NMR to find that magnetic field in terms of the proton precession frequency omega p. We take protons and put them in the same magnetic field, and we measure how they precess in the magnetic field. So basically, the whole experiment is a giant co-magnetometer experiment where we're measuring how muons precess relative to how protons precess in the same magnetic field. So to do that, to monitor the magnetic field, we have a series of 378 fixed probes. They're above and below the vacuum chambers where the muons are circulating. So they're not exactly where you want them, but they're pretty close. Close enough that you can infer between actual measurements that are made with a device we call the NMR trolley. So the NMR trolley is shown here. It's got an array of 17 NMR probes in it. And every 2 or 3 days, it pulls out, never having to break vacuum, and goes running around the inside of the storage ring, making measurements of the magnetic field so it can map what is the field here where the muons actually live. And you can see in this picture sort of these electrostatic quadrupole plates that provide the vertical confining field. And you can see these rails that the trolley rides on when it makes its measurements. And here you can see snapshots of the map of that field being made as the trolley is traveling around. So we measured every 2 or 3 days with this. We interpolate with the fixed probes. But in the end, we also need to know the absolute magnetic field that the muons are in. And for that, we use a whole series of absolute calibration probes that we effectively cross-calibrate every probe in this trolley with. We do that before every run every year and at the end of every run every year. And, it's been so consistent for 4 years in a row now we debated this year whether we needed to do it again. But, of course, this is the year where something would change and you wouldn't know about it. But it's been rock solid on the calibration for 4 years running now. One other interesting point is that at the Brookhaven experiment, they used this spherical absolute probe, spherical water sample to determine their absolute magnetic field. This probe was the same one that was used at Los Alamos. And so it allows us for the muonium hyperfine measurements, which provide some important inputs to our experiment, as we'll see in a moment. And you could have always asked at Brookhaven, how well do we really understand that absolute probe? In our experiment, we went out and we built cylindrical probes that are just as precise, and we've cross-calibrated with the original Brookhaven probe that was also used in Los Alamos. And again, the agreements are fantastic. Finally, one of our groups has been working on helium-3 magnetometry, which is a very different beast, because instead of having a liquid proton target, which has a self-shielding interaction that's fairly large, a gaseous helium-3 doesn't have that problem. And once again, all three of these probes are just in agreement at the sort of 10 part per billion level or better. So, I said we need to determine the precession frequency, that's omega A. We need to determine the precession frequency of those protons, and we do that at a particular temperature. That's actually a temperature dependent measurement is what this T reference means here. So this is what we need to determine. But then to convert this precession frequency of protons into an absolute magnetic field, and to take care of the fact that there's some other constants in there, right? Like if you remember the earlier equation, it has things like the charge to mass ratio of the muon. We rely on a number of values that come from co-data. And if you break it down without going into detail about it, this is the sort of set of basic fundamental quantities that we've measured with very high precision that we use to convert this into an absolute magnetic field. And the scale to keep in mind here is the goal of the experiment is to get to 140 parts per billion, 100 ppb stat, 100 ppb systematic, and all of these other measurements in total have an uncertainty of less than 22 parts per billion. So they're also fairly far from being controversial. Okay, so for the analysis big picture, in simplified terms, what we need to do is determine omega A over omega P, the magnetic field, the proton spin precession frequency. But then once we have those two frequencies, we have this map. We know muons only populate a certain part of the ring. So you have to convolve this map with the part of the phase space that the muons sample. In order to do that, we have two in vacuum straw trackers. This is another major upgrade from the Brookhaven experiment. There was one outside the vacuum straw tracker that had about a 40% uptime and had numerous difficulties, but in the end did what we needed it to do for Brookhaven. Now we have these two stations with just these gorgeous in vacuum straws. Here you can see the tracks coming through. And it's the very similar technology that's being used for the mu-to-E detectors, for those of you that might work on that. But we've just had amazingly good results with these detectors. They were robust from the day we turned them on, and they've just been amazing. I was skeptical, we're talking about, are we going to be able to make all these straws work in a vacuum without destroying the vacuum? And, they really pulled it off. This was done by a bunch of our British colleagues, some colleagues at Fermilab as well, and amazing. Anyway, so with that tracker, you can see, although the trackers measured the positrons, you can trace the arc of the positrons back to, the point of tangency on the circle the muons would have been on. That doesn't mean that tells you exactly where the muon decayed, but from that, you can map that, fairly trivially through simulation, that quantity to where the muons actually were. And so what you see here is the beam dynamics inside the storage ring. You can see the beam swimming radially. You can see it if you look carefully, breathing vertically. And this is all the motion that complicates extracting that omega A precession frequency. And this is, again, one of the huge upgrades relative to Brookhaven, is that we have all this beautiful live diagnostic 100% of the time of what the beam dynamics are doing inside the storage ring. That expression I said earlier, this tilde now means, imagine you've already done the convolution with the muon distribution. We write it like this simply, but there's really quite a few. It's really quite a bit more complicated. First of all, there's a clock frequency. We have a clock that ticks at a certain frequency. The precision of the clock is so much better than we would ever need that it's also not controversial, but it allows us to do something interesting in terms of blinding that I'll come back to later. We need to determine omega A, but there's corrections to that that come from the fact that we have an electric field. There's a pitch correction for the fact that muons aren't always traveling perfectly orthogonal to the magnetic field they're in. There's a correction for the fact that some muons can get lost from the ring as opposed to decaying to positrons that we detect. And then there's a correction called the phase acceptance having to do with how the beam couples to the calorimeter. In the denominator, you can see we have the field calibration, that absolute calibration with the plunging probe and those absolute probes I talked about. You have the determined map of the magnetic field that comes from the trolley. And then you have, in addition to that, a couple of corrections, because when we first inject the muons, we have two things that happen that are time dependent. First of all, we have a set of electrostatic quadrupoles that turn on for the duration the muons are stored, and then they turn off in between muon fills, because otherwise they would spark if you left them on high voltage nonstop. Also, every muon bunch that gets injected, we need to give it a kick to get it onto an orbit where it actually goes in a nice circle at the center of the storage ring. And so when you do that electromagnetic kick, it creates eddy currents. So during the time the field is making all these other measurements, mapping the field, monitoring the field, those systems are a little too slow to see things like a transient because the quads are turning on, or an eddy current because the kicker is just fired. And so we need to determine those separately and correct for those as well during the time the muons are stored in the storage ring. Oh, sorry, I just went through these. I should have gone through the slide. E-field, pitch correction, muon loss, phase acceptance, calibration, and then these transients are sort of the things we have to understand. And this, I have to say, is where the work is. This is why it takes 3 years to go from your first physics data to a physics result, really making sure you understand all these corrections in detail and you've determined them to the best extent possible is really where the time gets spent. So how much detail does it take? Well, I don't have time to go through it in a colloquium. I'll go through a couple of them in just a minute. But you can see here's a table of all the various systematics that are related to the extraction of that omega A precession frequency. And the main thing to say, these are all in ppb. And so the main thing to take away when you look at this is, you can see there's 4 columns because in our very first year of running, we ran the experiment in about 4 different configurations as we were trying to get it to run smoothly. So we ended up analyzing those in 4 different data sets. But you can see if you look at the size of these systematics, for the most part, they're all well below the 100 ppb that we're aiming at for the total systematic error, with the exception of a couple, and I'll talk about those in just a minute. But of course, this isn't all. This is just the ones for the omega A. We also have the denominator, and that's the numerator part there. So there's also all the analysis that has to be done to understand the systematics with extracting the magnetic field, the precession of the protons. And here you can see all those numbers also. And again, they're in really good shape on the field, with the exception of some transients that we'll come back to in just a second. So if you'd like to know a lot more details, this is one of the things that I'm pretty proud of. We managed to publish this result early in the year. And on the same day we announced the physics result to the world, we also dropped on the archive and had ready to be published in the journals 4 articles. One dedicated long article on how the beam dynamics impact the extraction of the result, one on how the magnetic field measurement is performed, one on how the muon spin precession frequency is extracted. Those are 3 long papers that we constructed from those 3 various sources of potential systematics. And then of course there's the PRL, which documents the result itself and ties everything together. That was a first for Physical Review to publish 4 articles simultaneously and try to keep it all secret from the community at large so we could make a big splash. So these are the final uncertainties from the analysis of our Run 1 data. You can see we achieved overall 462 parts per billion in our overall uncertainty on the extraction of the anomalous magnetic moment. That compares to Brookhaven that was at about 540 parts per billion. We're still vastly dominated by the statistical error because this Run 1 result is really just a small set of the statistics that we intend to collect, in fact, that we even have collected. The systematic errors totaled 157 parts per billion, so you'll note they're not quite reaching the 100 part per billion that we want for the ultimate precision of the experiment. And as I mentioned earlier, the co-data inputs all contribute at sort of a 25 part per billion level, which ends up being negligible in this quadrature sum. So the results are vastly dominated by statistics, and we need to do a little better on the systematics. And you can see with the systematics, I've underlined two of them here in particular. You can see there's the phase acceptance correction here, which is 75 parts per billion. And then there's one that we call BQ, which is the quad transients, which are 92 parts per billion. Were it not to these two, we would basically be at our goal already. We're going to do better on a few of these other ones as well. But basically, these are the two that we need to tackle. And luckily, they both became as large as they were because of a problem we had in run one. Okay, so to talk about the quad transients, first of all. So recall, we need this electric field to keep muons vertically confined. Our quads pulse on, and and we inject particles at about, I said 10 hertz on average, but really we get like 8 bunches in a row that are spaced at 100 hertz spacings. So the quads pulse for every one of those 100 hertz. When those quads pulse, it turns out they induce mechanical vibrations, which then makes an oscillating conductor in the magnetic field, and that perturbs the magnetic field. So we had to build special NMR probes really to map this effect and understand it. It was a long process. It took us a year to really develop the instrumentation, make the measurements, convince ourselves that we really knew what was happening. Because you can see, this is the size of those perturbations. It's plus or minus 300 or 400 part per billion, which is large. These little gray windows here are the windows in time when the muons live in the ring. And so we really needed to know that we could reproducibly understand what those field perturbations were during the time that the muons were in the ring. And so that took quite some time. Overall, the correction for run one turned out to be 17 parts per billion. But because we hadn't fully mapped this effect as a function of 2 pi around the whole ring, it ended up with a 92 part per billion overall uncertainty. Just based on the updated, more thorough maps we've made since this result came out in April, the ones we made over the summer, the ones we were still analyzing actually when the first result was published, we now know that this uncertainty is falling to something like 30 or 40 parts per billion with our next publication. So that looks like it will be in good shape. The phase acceptance, this relates to, in general, something we always worry about with this experiment. So this wiggle plot you can see here can at its sort of most basic level be described with a 5-parameter function. Of course, by the time you include beam dynamics and everything else, it really takes something like 27 parameters to get the chi-squared you see in this bit. But it's approximately just an exponential decaying envelope times this frequency modulation coming from the muon spin precession. And for illustrative purposes, you can ask the question, this phase is determined by the initial phase of the muons when they enter the storage ring. But what if for some reason that phase wasn't constant? Well, if you just do a simple Taylor series expansion here, where you have phi naught become, phi become phi naught plus phi prime of t, you can see you could recollect phi prime, and that would be, that would change what you thought omega A was in a very insidious way, that by fitting the data, you would never see it in the chi-squared. The phase would just be ever so slowly linearly shifting, biasing your extraction of omega A. So we worry a lot about, is there some way that we can have that phase shift? And to give you an example of how that could happen, imagine for a moment there were no C particles. There weren't these virtual particles. And whenever you injected your muons, their phase stayed locked forever with respect to their spin phase, stayed locked forever relative to their momentum. But imagine we lose, say, 1/3% of the muons during the time that we're monitoring them going around the ring. Imagine for some reason those 1/3% of the muons at injection had on average a different phase. Say their phase pointed this way and the muons that stayed in the ring pointed this way. Well, as you lose these, the muon spin vector would rotate ever so slightly. And that shows you kind of intuitively why we have to worry about whether this phase can change and the sources where you can get a changing phase. So the way this comes in is the decay positrons that we detect do end up carrying a particular phase. That phase depends on both the X and Y position that the muon, where the muon was in the ring when it was born, as well as the energy of the decay positron. Because lower energy decay positron, if you have, even if the muon spin is perfectly forward with respect to the momentum, you can have a decay that's off axis angle and just gives you a smaller a smaller positron energy. So there's an energy dependence to the phase, and furthermore, there's an XY position dependency. This XY part isn't a big deal as long as this energy one is well known. It's been analyzed forever since CERN in the 70s. But this XY position becomes a problem if for some reason the beam isn't stable in the gap. As long as it doesn't change over the measurement period, we don't care. But if it starts to shift, then that causes a shift in the phase, and that causes the problem that we're most worried about. And that's exactly what happened. So decay positrons are born from a muon, a particular muon. Each calorimeter samples an ensemble of those phases. And so you can sort of intuit that from this picture. So any movement of the muon beam, if the muon beam moves outward, you can see suddenly the muon beam will miss this detector, and it will change the average phase of the muon ensemble that the detector sees, not because the detector changed, but simply because the beam moved in the gap. So the problem we had with run one is we had some equipment failure. In those electrostatic quadrupoles that keep the vertical confining field, they're supposed to be on and stable before we inject beam. But because we had a few resistors that burned up and couldn't be conveniently replaced for the run, this shows the electric field turning on in kilovolts as a function of time. And this is sort of in microseconds, you can see down here. We'd like to start the fits for the physics data at about 30 microseconds where this red dashed line is. And you can see these failed resistors led to a time dependence where the beam was both dropping down vertically in the storage ring during the measurement period. And more importantly, its width was also changing as the strength of that focusing field changed as the quads turned on. And so you can see with this map here, if you go up or down, it's not quite as important because this is a plot of the average phase depending on the XY position. So if your whole beam moves up a little, you get a little more purple here, but you lose a little purple here. And the first order, it kind of cancels out. But if the beam squeezes down, now you have a first order change in the phase relative to this phase dependency on the XY position. So we fixed those resistors by run two, so the beam doesn't do that anymore. So this whole phase acceptance error will essentially go away. It was a 158 part per billion correction for run one with a 75 part per billion uncertainty, and the residual correction with the equipment failure fix is now projected to be something like 20 ppb or so. So that's very much under control also. So as I mentioned earlier, we have this clock frequency. This leads to a very interesting way we do our blinding. It's in particle physics, we like to do the analysis blind so we don't have some sort of unconscious bias. And so the way we do that is we simply have this clock behind a locked door and we set the frequency the clock ticks at, and we don't tell any of the analyzers what that frequency is. Not even the spokespeople know. In fact, we had two members of the Fermilab directorate whose job it was to come out every week, open the cabinet, log that everything looked okay, the frequency generator was still ticking along at the frequency it was supposed to, and they're really the only people who ever interact with the clock. And in fact, they also provide the initial setting for the clock that none of the collaborators know. Of course, we do have monitoring equipment. We beat this clock against another clock that we don't know, and we monitor that difference frequency just to make sure, while these guys are on vacation, we know if something changed, even if they're not checking the clock every day. So on February 25th of this year, our collaboration, which is about 200 people, gathered to unblind. The other important function that those two directorate people do is they make envelopes with the frequency in it. And so here's one envelope that we stored in Seattle, one we stored in Fermilab. This is the unsealing of the envelopes. You look at the frequency the clock is at, you type it into your JavaScript. You used Excel at Brookhaven, but whatever, it's a new world. And out pops the result that everybody's been waiting on for 10 years and working hard at analysis for 3 years. And this is what we saw. So this is the Brookhaven result. The little tick marks here show the statistical error, and the outer bands show where the systematic, the total band is the total error, and the tick marks show the statistical part of it is the right way to say it. Once we unblinded, this is what we saw. And I can't tell you, of those 200 people, there's about 10 of us that were part of the original Brookhaven experiment. And I can't tell you what a relief it was to see that number pop out from the blinded envelopes and appear on the screen and be basically in beautiful agreement with the Brookhaven experiment. This is despite an experiment that's been upgraded to be much better. You could argue you're using the same container, but even the container has a 3 times more uniform field than what it did at Brookhaven. And so for all the systematics that mattered at Brookhaven, the experiment had all new equipment to address those systematics more directly. And so that was really, really great to see. So with the good agreement between them, you can average the two. That's what the average result is for the 2 experiments now. Oh, and the one thing to point out is, our error, even though it's not much better than Brookhaven, it was slightly better than Brookhaven. And so if you look at the experimental average of the 2 and you compare that to the theory initiative prediction, which remember is from this data-driven approach, they're still sorting out this lattice controversy and whether what the lattice is going to say going into the future. But that difference between the data-driven approach and the experimental world average is 4.2 sigma, which I hope Ryan Patterson asked me a question because we can talk about that. Now I'll just say it. My buddy Ryan, who I worked with for many years on Miniboon, tells me this, you can't really say this because we know there's a giant look elsewhere effect. We only build follow-up experiments once a result is over 3 sigma. And so that there's to really say 4.2 sigma. To that, Ryan, I have 2 points to make. One is that when we originally proposed the Brookhaven experiment, we wanted an overall statistical error of an overall error on the experiment of 350 parts per billion. And with the Fermilab combined result, our experimental error is now 350 parts per billion. So you can just consider this part of Fermilab the continuation of Brookhaven to achieve the Brookhaven initial goal. But seriously though, what really matters here is that we're going to cut our error down by another factor of 4 before the experiment is over, and then it won't matter whether you combine with Brookhaven or not. Okay, so in conclusion, we've determined the anomalous magnetic moment to this unprecedented precision of 460 parts per billion. It's only 6% of our ultimate data sample. By itself, it's at tension with the standard model at 3.3 sigma. Combined with Brookhaven, that tension rises to 4.2. And the big news here is really after 20 years, we've been able to confirm the Brookhaven experimental results. And the outlook is really much more data is coming. This is our data collection plot. Run 1, this publication was about 6% of that data set. Run 2 and 3 is being analyzed right now. We're expecting to publish that next year. We were hoping by summer, it might be fall, but anyway, the analysis is coming along and the systematics look great compared to run 1 so far. Run 4, we finished this run at about 12 times BNL, and run 5 is starting basically this week on the way for our goal to get to 20 times BNL. We might not get fully to 20 if MUDE gets ready to turn on. We might only get to 18 or 17, but it's going to be close, and it'll be close enough to our statistical goal. And I think that's it. I'll just say thank you very much. Sorry for running over a little bit.
All right, Chris, I hope we could hear the applause from the in-person group here in the Bridge Lecture Hall. Thanks for a very interesting talk. We have time for some questions. For the remote people, you can use the chat window or raise your hand. We can unmute you. For the people here in the audience, you can just raise your hand and ask, and I'll repeat your question. Yes, back there.
So you went through a lot of difficulty to move the storage ring. Why not build a new one?
Oh, did you hear that by chance, Chris?
I could hear that just fine. Thank you.
Great.
Yeah, that's an easy one. The estimate to build the new one was about 20 million. The estimate to move the old one was 3.
Did the costs bear out in a way that you estimated?
Actually, it was really good. We very early in the experiment, we estimated that it was going to be about $3 million to move this ring, and we ended up spending about 3.3 million. So considering how early we were when we started telling the DOE those estimates, I'm really proud that we ended up within 10%. Now, when we first started proposing it, we also told the DOE we were going to fly it with a helicopter. That didn't work out so well because it turned out the fly time of a Sikorsky carrying, even if you split those rings into 3 separate rings, you got about 10 minutes of fly time. So you would have had to leapfrog it 50 times across the United States or something. So anyway, that part didn't work as we planned, but the cost ended up being pretty reliable. Now, and the other part of it was, of course, the schedule. the construction of that storage ring at Brookhaven took, easily 5 years. And our goal was to get this experiment online and run before MUDE was ready. So we appreciate the delays in the solenoid schedule.
Any other, I see a hand raised
All right.
from
So-
Brad Philippone.
Hey, Brad.
Hey, Chris. Great talk.
Thanks.
Yeah. You mentioned the increased data that you're going to take. If you sort of pseudo include the look elsewhere effect, are we talking if the value doesn't change, are we talking 10 sigma at the end?
Right.
Okay.
Let me explain. Let me tell you what's going to happen there. Well, of course, we know what's most likely to happen there is we'll be stuck in 3 sigma forever, as anybody who's worked in sterile neutrinos and other anomalies know. But actually, seriously, what would happen if that world value chain stayed unchanged and the theoretical prediction stays unchanged? Then we will be just above 5 sigma. And that's because the theory initiative really, in terms of that data-driven approach, the size of their error bar, they made every conservative assumption they could in that data-driven approach. And so that error bar, suddenly that had been getting smaller and smaller and smaller, with the recommendation from the theory initiative grew again, because their goal was to produce a number that they thought was conservative and one that you could believe. And so we're going to get another factor of 4 reduction in the experimental error. But it's really going to hinge, the ultimate significance is going to hinge on the theory catching back up again in some sense, because they've lost some ground with this theory initiative recommendation. And so if we assume the theory doesn't change and we just go down by a factor of 4, then we're sort of right above that 5 sigma, 5.1, 5.2 sigma level. And then, of course, the other caveat in there is, will the theory value shift? Will we learn something from the lattice that somehow impacts the data-driven approach? Are we learning that there's something wrong with the data-driven approach that we haven't discovered before? So that's where it'll stand. Unfortunately, we're going to be a little bit of time, I think, understanding the theory again.
All right. Any other questions here or remotely, locally or remotely?
I told you it was going to get dark here.
Oh, sorry, was someone saying something?
Yeah, so we have one from Ryan. I'm going to ask him to unmute.
Hi, Chris, you hear me?
Yeah, I can, Ryan. Good to hear you.
Great. Yeah, great talk, Chris. One of the features of the experiment is extreme uniformity and stability, and measuring any deviations from that. Is there any plan or concept of intentionally deviating, either lowering the E field or something to let the beam be a little bit messier, something to check that your estimates of those aspects of the experiment are accurate?
Mm-hmm. Yeah, I mean, for a lot of those things that you would think about doing, you end up running into the problem that to do them precise enough, you need, another 20 times BNL sample to compare to your other 20 times BNL sample, unless you have a known systematic, that you can make 10 times larger. And so we do that. We do that where it's possible. Just to give you one example, I mentioned earlier that we were worried about if those muon losses have a different phase. And we do know there's a way for muon losses to have a different phase. There's a momentum dependence. The muons that have a slightly, we still store, we don't get just 29.3 gamma muons. We have a range, plus or minus 0.15% at 1 sigma of muon momenta. And we know, based on the way the beam develops beforehand, there is a phase dependence. The initial muon phase entering the ring does have a momentum dependence. And so one of the things we did, as an example, was we tuned the ring to run, a 0.5% high in momentum to store the portion of the beam that's a 0.5% higher or 1% higher in stored momentum, and we did -1% lower. And that's really a beautiful talk. If this wasn't a colloquium, if this was a seminar, this is one of the things I'd certainly be talking about. But it was just gorgeous because we were able to predict from the simulations what that momentum dependent phase should be. Then we went out and designed a way to determine it in the experiment and found exactly the phase, the momentum dependence we expected from the simulation. So we do things like that, and I could probably list another 2 or 3 examples. So we do it where we can, and yeah, so we do. One interesting thing that we're going to do this year, which I find particularly interesting, there's a whole class of systematic errors that come from the coherent betatron oscillations, and for the first time in the history of g-2 experiments, these storage ring experiments, the ones at CERN or Brookhaven or even Fermilab, we're going to deploy an RF system this year that turns on in the first few microseconds the muons are circulating, and it will damp those CBO oscillations by a factor of 5, almost to being negligible. And so it will be interesting to do this analysis with a very large sample from run 5, where we've dramatically changed the beam dynamics inside the storage ring. We also are proposing to run mu-, where we flip the polarity of every element of the beam line. We flip the polarity of the storage ring. We would like to do that in run 6. We're kind of debating here to see what the schedule from U to E is going to look like. But the problem with that is we really consider that more of a CPT test, because we don't have any systematics that we think that polarity flip will elucidate. Although, sometimes the community likes to see things like that. They're like, oh, you flip the polarity, you got the same answer. But in reality, the motivation to do that is more just to have a measurement of the negative muon to go with the positive muon.
All right, any final questions?
Yeah,
from Bridge or remotely?
I'm gonna unmute Brad one more time.
Thanks. Yeah, I had just a fitting question, Chris. You mentioned 27 parameters to fit the omega A, and it looked like your chi-square, I didn't check it, but I'm sure your chi-square per degree of freedom is pretty probable.
Yeah.
How many, did you have to add any parameters from the Brookhaven result to do that, or was it the same or less? Just,
I think essentially we probably could have gotten away. Okay, so all of the fundamental physics parameters that were used at Brookhaven, we used again here. The problem is we had to add a few parameters because, unlike Brookhaven, we had that problem with the resistors and the electrostatic quads, which created a new sort of exponential time dependence that Brookhaven didn't have to contend with. And those are essentially the only meaningful parameters we had to add.
great, thanks.
As we go up in statistics, however, there are higher order beam dynamics, like things like the vertical waste, where how the beam breathes in and out. That's a type of coherent betatron oscillation that decays away much faster with like a 5 or 7 microsecond lifetime. And so when you start your fits at 30 microseconds, it's basically over. But as you go up in statistics, you start to see that more in the Fourier transform residuals and in the chi-squared. And so, and we know fitting run 2 and 3 already with sort of 4 times the statistics that we're having to add some of those terms. Let me say that I'm sorry I ran over a little bit. I'm happy to hang out here if you guys want to let everybody else go. And if anybody has more questions, or students or postdocs, want to chat more like we would have normally done had I been there after the colloquium, I'll hang out. I'm happy to hang out if people want to talk more informally. So.
Okay, yeah, that sounds like a good plan. So maybe let's all thank Chris again. Just like in a in-person colloquium, we'll just leave the computer here at the desk as Chris, and you can come up and chat with Chris if you like. But otherwise, we hope to see you next Thursday.